Welcome to the Ethernet Fundamentals Unit. In this unit, we'll cover the basics of Ethernet technology and understand how data is forwarded in an Ethernet network. We'll start with Ethernet technology evolution and standards. Later on, we'll detail some Ethernet specifics, such as how Ethernet nodes are identified using MAC addresses and Ethernet frame structure. Then, we'll describe how Ethernet switches build and maintain their forwarding tables called MAC address tables that are used to forward frames in the network. Ethernet operates in the data link layer and the physical layer of the OSI model. The data link layer provides the functional and procedural means to transfer data between network nodes and the means to detect and possibly correct errors that can occur in the physical layer. The physical layer defines the electrical or optical properties and the transfer speed of the physical connection between network nodes. Ethernet has become the predominant LAN technology thanks to its ability to evolve and deliver higher levels of performance while also maintaining backward compatibility. Ethernet is designed to suit the needs of a broad range of applications, ranging from home networks to corporate LANs to data center interconnects. Naturally, each type of application has unique requirements and protocols that it needs to support. Ethernet was introduced in the 1970s by a team led by Robert Metcalfe at the Xerox Corporation's Palo Alto Research Center in California. In the mid-1980s, the Institute of Electrical and Electronics Engineering, IEEE, published a formal standard for Ethernet defined as the IEEE 802.3 standard. This standard defines rules for configuring an Ethernet network and specifies how the elements in an Ethernet network interact with one another. By adhering to the IEEE standard, network equipment and network protocols from different vendors can communicate efficiently. Ethernet's original 10 megabits per second throughput increased to 100 megabits per second in the mid-1990s, and currently it supports up to 400 gigabits per second. Ethernet allows nodes that are connected to the same LAN to communicate with one another by sending Ethernet frames to each other. In order to achieve this, Ethernet nodes must be identified with a unique address, known as the Media Access Control Address, or MAC. Every Ethernet frame that is generated by the sending node contains a source and destination MAC address in its header. The frame is then forwarded based on where the destination node resides. A network interface card, or NIC, is a hardware component that connects a node to the network. The NIC allows nodes to communicate over the network, either by using cables or wirelessly. The NIC is both a physical layer and data link layer device. At the physical level, it provides access to the physical medium. At the data link level, it provides a low-level addressing system using MAC addresses. A media access control address is a unique identifier assigned to a network interface for use as a network address in communication within a local network. A MAC address is burnt on the network adapter's hardware by the vendor. The Ethernet standard requires that every Ethernet vendor register with IEEE and to be assigned with an OUI, organizationally unique identifier. MAC addresses are 48 bits long, represented in 12 hexadecimal digits. They have two halves. The left 6 digits form the OUI, and the right 6 digits form a serial number assigned by the vendor. Combining a unique OUI and a unique serial number yields an address that uniquely identifies an Ethernet interface in the network. You can use the following commands in order to identify MAC addresses of network interfaces. On a Linux system, use the ifconfig command. On a Windows system, use the ipconfig command. The MAC address is listed as a series of 12 hexadecimal digits, where each pair is separated by either a dash or a colon. The data link layer is responsible for data transfer over the physical medium, hence an Ethernet frame that can be carried over the Ethernet network created. The Ethernet standard defines the structure of an Ethernet frame as follows. Payload, the protocol data unit received from the upper layer. It's the part that is encapsulated with the layer 2 header to construct a frame. The header includes 3 fields: destination MAC address, which specifies the node for which the frame is intended; source MAC address specifies the node sending the frame; and type field, also known as ether type, which indicates the upper layer protocol type, such as an IP version 4 packet. There is another type of frame that has a length field instead of the Ether type, but it won't be discussed here. Ethernet also adds a field called frame check sequence, or FCS, to the end of the frame. The FCS is used to detect corrupted frames. Generally, when corrupted frames are dropped, Ethernet doesn't retransmit them. This is the responsibility of upper layer protocols such as TCP. The number listed under each field represents its size in bytes. We've just seen the structure of a standard Ethernet frame, which is composed of a payload encapsulated with a layer 2 header and trailer. In addition, the standard also defines that the payload size is in the range of 46 to 1500 bytes. The maximum payload size is also referred as the maximum transmit unit, or MTU. Frames with more than 1500 bytes payload are considered jumbo frames. Jumbo frames are not a standard, though supported by some vendors. Adding the 14-byte header plus the 4-byte trailer results in an overall Ethernet frame size in the range of 64 to 1518 bytes. Any frame less than 64 bytes in length is considered a collision fragment, or runt, and is automatically discarded by the receiving nodes. In order to understand how Ethernet frames are forwarded in the network, we first need to understand the role of Ethernet switches in networking. An Ethernet switch is a hardware device with multiple ports that connect Ethernet nodes. There are different types and sizes of switches, with different number and speed of ports, depending on the switch vendor and specific model. Ethernet nodes may have one or more Ethernet switches connecting between them. So, how are frames forwarded from a node with MAC A to the node with MAC B that have a single switch between them? When node A generates an Ethernet frame and sends it on the wire, that frame is received by the switch. The switch needs to learn where MAC B resides, or in other words, on which of its ports the frame should be sent. It seems like an easy task if both source and destination are directly connected to the switch. But what about nodes that have multiple switches between them, like nodes B and F? In this scenario, the switches need to know the whereabouts of nodes that are not necessarily directly connected to them in order to successfully forward the frames in the network. An Ethernet switch forwards frames based on the destination MAC address in the frame. But in order to be able to do so, it needs first to identify where those MAC addresses reside. The learned MAC addresses are stored in a database called the MAC address table that contains destination MAC address to exit port mappings. Let's see how MAC address table entries are populated, and then how they are used by the switch to forward frames. In this example, node A sends a frame to node B. The frame is received at the switch on port 1. The switch looks at the source MAC address and adds an entry that maps MAC A to port 1. Now if node C sends a frame to node A, the switch has a pre-learned entry for destination MAC A and the frame is sent on port 1. Dynamically, learned entries have an aging time, meaning if they are not used within a defined time, they are flushed from the table. Ethernet switch vendors do allow the adjustments of the aging time. Also, static entries can be configured. Static entries are not aged out and will remain in the table until manually removed. We've just seen how the MAC address table is populated with destination MAC to exit port mappings that are later used for frames forwarding, but it happens occasionally that there is no matching entry in the MAC address table. Those frames are called unknown unicast frames. Unicast addresses represent a single interface in a network. So what does a switch do with unknown unicast frames? For example, when node A sends a frame to node D. In this case, the switch will flood the frame, that is, send the frame on all its ports except for the incoming port. Frames for which their destination MAC address have a matching entry in the MAC address table are called known unicast frames. They will be sent on the specific port. A broadcast address represents all nodes in the network as the destination. Broadcast frames are identified by a special MAC address where all bits are set to 1. The hexadecimal representation is all 12 digits set to F. When the switch receives broadcast frames, it floods them. A multicast address represents a selected group of destinations in the network. Multicast frames are identified by special MAC addresses, where the least significant bit of the first octet is set to 1. Traditionally, Ethernet switches don't have the logic to forward multicast frames to the designated group members, hence they are flooded. Traditional switching operates at layer 2 of the OSI model, where packets are sent on a specific switch port based on destination MAC addresses. Routing operates at layer 3, where packets are forwarded based on destination IP addresses. Often referred to as a multi-layer switch, a layer 3 switch combines the functionality of a switch and a router, thus adds flexibility to the network. There are different considerations of whether to design the network as a layer 2, layer 3, or a combination of both. We'll cover some of those in the next unit.